Creating a fracture does not guarantee production. That is the first rule. Fracture design is controlled by three components: fluid, proppant, geometry. Nothing outside these three defines the outcome. Now define each one precisely. Fluid creates the fracture and transports proppant. If transport fails, proppant never reaches the fracture tip. Now proppant. It maintains conductivity. After pumping stops, closure stress acts on the fracture. If proppant fails, the fracture closes. Now geometry. This defines reservoir contact. Length controls reach. Width controls conductivity. Height controls vertical coverage. Now connect them. Fluid enables placement. Proppant enables flow. Geometry defines exposure. If any one of these fails, the treatment has no value. Now read the statement on the slide. Failure comes from 3 points: insufficient geometry, proppant failure, or transport failure. This is not component design. This is a system. All three must work together. That is the objective of this lesson. Creating a fracture is not the objective. Improving production is. These are not the same. Now isolate the problem. 3 failure modes, each connected to one component. First, geometry failure. Fracture is created, but it is ineffective. Too short, so reservoir contact is limited. Too narrow, so flow resistance is high. Or out of zone, so it connects the wrong intervals. Now second, proppant failure. Fracture is created, but does not stay open. Closure stress crushes the proppant. Fines are generated. Pore space inside the fracture is blocked. Conductivity collapses. Now third, fluid transport failure. Proppant does not reach the fracture tip. It settles early, so the effective fracture length is much shorter than the created length. Now step back. 3 components. 3 independent failure paths. Now move to the framework. Each component has a defined role. Fluid creates the fracture and transports proppant. Proppant maintains conductivity. After closure, geometry defines how much reservoir is contacted. Now connect them. Fluid enables geometry. Proppant enables conductivity. Geometry enables production. If one fails, the system fails. Now read this slide correctly. This is not describing problems. This is defining how the fracture system must be designed. Proppant function is conductivity. Conductivity equals proppant permeability multiplied by propped fracture width. Now define controlling physics. First, transport requirement. Proppant must remain suspended during flow inside the fracture. Control variables: particle size, proppant density, fluid viscosity, flow velocity. Now define condition. Fluid velocity must exceed settling tendency. If not, proppant settles and accumulates. Now define failure sequence. Early settling. Proppant bank near wellbore. Outer fracture unpropped. Effective fracture length reduced. Now second mechanism. Proppant strength under closure stress. After pumping stops, normal stress increases on fracture faces. If proppant strength is lower than closure stress, grain crushing occurs. Now define consequences. Grain crushing. Fines generation. Migration into pore space. Pore blockage. Conductivity loss. Now third parameter. Particle size selection. Larger size. Higher permeability, but lower mechanical strength. Smaller size. Higher strength, but lower permeability. Selection is stress dependent. Now define stress requirement. Proppant strength must exceed maximum closure stress during entire production life, not initial condition. Now fourth parameter. Proppant concentration. Controls propped width. Low concentration. Insufficient fracture support. Partial closure occurs. High concentration. Increased carrying requirement. Higher risk of settling. Now define transport constraint. High concentration requires higher viscosity or higher velocity. Otherwise, transport fails. Now final statement. Proppant design is not material selection. It is matching, transport capacity, mechanical strength, and required conductivity. Proppant function is conductivity. Conductivity equals proppant permeability multiplied by propped fracture width. Now define controlling physics. First, transport requirement. Proppant must remain suspended during flow inside the fracture. Control variables: particle size, proppant density, fluid viscosity, flow velocity. Now define condition. Fluid velocity must exceed settling tendency. If not, proppant settles and accumulates. Now define failure sequence. Early settling. Proppant bank near wellbore. Outer fracture unpropped. Effective fracture length reduced. Now second mechanism. Proppant strength under closure stress. After pumping stops, normal stress increases on fracture faces. If proppant strength is lower than closure stress, grain crushing occurs. Now define consequences. Grain crushing. Fines generation. Migration into pore space. Pore blockage. Conductivity loss. Now third parameter. Particle size selection. Larger size. Higher permeability, but lower mechanical strength. Smaller size. Higher strength, but lower permeability. Selection is stress dependent. Now define stress requirement. Proppant strength must exceed maximum closure stress during entire production life, not initial condition. Now fourth parameter. Proppant concentration. Controls propped width. Low concentration. Insufficient fracture support. Partial closure occurs. High concentration. Increased carrying requirement. Higher risk of settling. Now define transport constraint. High concentration requires higher viscosity or higher velocity. Otherwise, transport fails. Now final statement. Proppant design is not material selection. It is matching, transport capacity, mechanical strength, and required conductivity. Fracture geometry is defined by three dimensions: length, width, height. Now define them. Length controls reservoir drainage. Longer fracture increases contact area and improves inflow. Dominant variable in low permeability formations. Now width. Width controls fracture conductivity. Conductivity depends on proppant permeability and propped fracture width. If width is too low, flow resistance increases. Fracture becomes a bottleneck. Now height. Height controls vertical coverage. Fracture must remain inside the target interval. If height grows beyond boundaries, non-productive zones are connected. Now define control variables. Injection rate controls fracture length. Higher rate increases fracture propagation. Fluid viscosity controls fracture width. Higher viscosity increases net pressure and increases width. Formation stress contrast controls height. Higher contrast limits vertical growth. Now define trade-offs. Long fracture. Increases reservoir contact requires higher fluid volume, increases risk of growth beyond target. Wide fracture. Increases conductivity, requires higher viscosity or proppant loading, increases treatment cost. High fracture. Increases vertical contact, increases risk of zone communication. Now define optimization. Performance depends on balance between fracture conductivity and fracture length. If conductivity is too low, fracture limits flow. If conductivity is too high, excess design with no productivity gain. Now define design target. Optimal condition requires minimum resistance inside fracture balanced with reservoir inflow capacity. Low permeability, prioritize fracture length. Moderate permeability, balance length and width. High permeability, prioritize fracture conductivity. Now define constraint. Fracture must remain inside target interval. This condition overrides all optimization. Now final rule. Geometry is not maximized. Geometry is balanced based on permeability, stress profile, and conductivity requirement. Fracturing performance is controlled by interaction. Fluid, proppant, and geometry do not act independently. Now define interactions. Fluid and proppant. Fluid viscosity controls transport capacity. Low viscosity with high concentration. Leads to early settling. Proppant deposits before reaching fracture tip. Effective prop length is reduced. Now fluid and geometry. Injection rate controls fracture length. Fluid viscosity controls fracture width. Low viscosity supports long fractures, but limits proppant placement. High viscosity improves placement, but reduces fracture extension. Now proppant and geometry. Proppant distribution defines effective geometry. Created fracture length is not equal to effective propped length. Unpropped sections close after pumping. They do not contribute to flow. Now define failure conditions. Case 1. Low viscosity with high proppant concentration. Transport capacity is insufficient. Proppant banks near the wellbore. Outer fracture remains unpropped. Now case 2. High viscosity with insufficient volume. Proppant is transported correctly, but fracture length is limited. Reservoir contact is reduced. Now case 3. Incorrect proppant strength. Closure stress exceeds material strength. Grain crushing occurs. Fines are generated. Conductivity is lost. Now define system condition. All three must align. Fluid must transport. Proppant must resist stress. Geometry must match reservoir. If one fails, the fracture loses effectiveness. Now final rule. Created fracture does not define performance. Effective conductive fracture defines performance. Fracture performance depends on conductivity distribution, not fracture size. Now define correct condition. Proppant is distributed along the full fracture length. Conductivity is continuous from wellbore to fracture tip. Flow into the fracture is uniform. No internal restriction exists. Result: maximum effective fracture length. Maximum productivity improvement. Now define failure condition. Proppant is concentrated near the wellbore. Outer fracture contains no proppant. Conductivity is limited to inner region. Outer fracture closes after pumping. Now consequence. Created fracture length is greater than effective fracture length. Only the prop section contributes to flow. The remaining fracture is inactive. Now define comparison. Short fracture with uniform proppant distribution delivers higher performance than a long fracture with poor distribution. Now final rule. Fracture geometry without conductivity has no value. Conductivity distribution defines performance. Fracturing design is a coupled system. Fluid, proppant, geometry. All three must be correct at the same time. Now define each rule. Fluid must satisfy transport and pressure requirements. Without transport, proppant does not reach fracture tip. Now proppant. Proppant must withstand closure stress. Without sufficient strength, crushing occurs. Conductivity is lost. Now geometry. Geometry must match reservoir permeability. Incorrect geometry creates either insufficient reach or flow restriction. Now define interaction. Fluid controls transport and width. Injection rate controls length. Proppant defines conductivity. Geometry defines reservoir contact. All variables are dependent. Now define final condition. Effective fracture is defined by conductive length, not created length. Now final rule. Maximum size is not the objective. Optimal conductive geometry is the objective. This is the complete fracture design system. Fluid, proppant, geometry. All three are integrated. Now the core structure. Fluid defines pressure transmission, proppant transport, fracture efficiency. Proppant defines mechanical stability, conductivity, long-term performance. Geometry defines reservoir contact, flow efficiency, production response. Now the rule. All three must be designed together, not sequentially, not independently. Now the failure pattern. Transport failure. Proppant does not reach fracture tip. Strength failure. Proppant crushes under closure stress. Geometry failure. Fracture does not match reservoir requirement. Now system objective. Maximize effective conductive length, not created fracture length. Now use this as a checklist before any fracture design. Fluid must satisfy transport. Proppant must satisfy stress. Geometry must satisfy reservoir. Now move forward. Next step is execution control and real-time fracture monitoring.